Hello everybody, today is a third lecture in the course of descriptive set theory. An application to normal number.
And so we're going to go a little bit of a different direction today. So we're going to talk about something called the Cantor series expansions, and this is one of many, many ways to generalize the idea of a base B expansion. So let's just recall some simple things. Let's say we have something like, I don't know, 1/7. You're just repeating this. So what does this mean? Of course, this means, right, this is going to be 1 divided by 10. You have your tens place. And then you have 4 divided by 10 squared, plus 3 plus 2 divided by 10 cubed, plus 8 divided by 10 to the 4th, plus 5 divided by 10 to the 5th, plus 7 divided by 10 to the 6th, and so on. Right, so this is the, let's say at least in the US, the tens place. This would be the hundreds place. Markers. Let's see if one of these will work. And of course, this one is the thousands place, and so on. So, hopefully familiar to everybody, just thinking, way back. And so there are, let's say, some reasons that I'll get into where we can generalize what's going on here to have it where your base is changing potentially at every step. So let's instead look at something like the following. Let's say that let Qn be a sequence of integers that are greater than or equal to 2. And what if we look at some sort of expansion? Let's say that x is a real number, and I'll give a bunch of examples coming up. And I claim that we can write x in the form of a0 plus a1 divided by q1 plus a2 divided by q1, q2 plus a3 divided by q1, q2, q3, and so on. Where an is between 0, 1, and qn minus 1. And just for uniqueness, this really isn't that important. We can require that an is not equal to qn minus 1 infinitely often. Now we could also instead, or an is not equal to 0. And depending, there's two different expansions. So just like with the decimal expansion, you can have something like 1/4 can be 0.25000, or you can write it as 0.24999, and so on. Basically, if you put this restriction here, it prevents things like this from happening. If you put this restriction on, it prevents this, and then makes that happen. But it won't matter really for anything that we're looking at. I just want to have a definition for the Cantor series expansion. When I use the definite article the, that implies uniqueness. So we call, so this a0, point a1, a2, a3, and so on, is the Q Cantor series expansion of x. And I'll give some examples because I think it's very important here. So let's give some examples, and I'll actually give the original motivating example for caring about something like this. So let's recall that E is the sum from n equals 0 to infinity of 1 over n factorial. And right, we can rewrite this as 2 plus 1 over 2 plus 1 over 2 times 3 plus 1 over 2 times 3 times 4, and so on. So suppose that we have Qn equals n plus 1, and then we would get E is equal to 2.1111117. So in this particular base, the expansion of E is something very simple, just a bunch of 1s after a 2. And originally, Cantor, the same Cantor we know from set theory and all that sort of stuff, was the one who came up with this. That's why it's called the Cantor series expansion. And his original motivation was to extend things like this basic proof that E is an irrational number that goes on this sum right here. And so he had some conditions under certain special cases. Okay, thank you. Under certain special cases, this condition will give you that you have a irrational number with this expansion. Or under certain cases, you can get a rational number. Because think about like what we have in base B. We have this condition that a number is rational if and only if its base B expansion is eventually periodic. Right? So like this one I wrote before with 1/7. This is periodic, right? It's just 0.142857 and you repeat it over and over. And that's what decimal expansion or any base B expansion of a rational number looks like. An irrational number, it might still be very simple in a sense, but it's not going to be eventually periodic. Like, something along those lines like this one I mentioned before, sum of 1 over 10 to the n factorial. This is irrational, it's transcendental. It's mostly all zeros, but you get these 1s sprinkled in every once in a while and in a very non-periodic sort of way. But it's easy to see, okay, it's just at a factorial position, so you put a 1. So I want to mention just right now that this problem of coming up with some sort of fully general criterion on is a number rational or irrational based on, say, its Cantor series expansion is totally open, and probably there is no full criterion on this. Probably there are only going to be special cases. Like, this is something I want to work on with a set theorist co-author of mine in terms of maybe precisely trying to find a way to say that you can never actually fully, do a full characterization of this. But this isn't anything that's been proven or investigated. I mean, I would bet probably a pretty good chunk of money that there's no way you're going to ever have any sort of actionable criterion where you can always determine if a number is irrational or not just based on its Cantor series expansion when you're allowed to pick any possible base. So for some bases, for example, rational numbers have finite expansions, and if your expansion's not finite, when I say by finite, I mean it has an expansion terminating in all zeros. But anyways, this isn't my interest in this. This was Cantor's original interest, and there's still papers being published on this type of thing every now and then, and some of them are pretty interesting results. I care more about normal numbers, but this is still, something of interest. There also have been, I believe, 2 papers. I'm the co-author of one of them. Maybe there's some more, but Vikesh Kumar, my co-author in India, I forget, he's at one of the IITs now. He was in Allahabad when I worked with him. And then he moved somewhere on the west coast, I think near Goa in India. And I plan to visit him, but I haven't done it yet. And this is in his new location. But he's dealing more with transcendental numbers, and he had some criterion under which a sum of this form can give you a transcendental number. But dealing with transcendental numbers is something very hard, so there's even less of like any chance of hoping to identify if a number is transcendental or not based on its expansion. Just in some special cases you can. I want to give another example. Let's suppose that, so we have this, and this is called like the, sometimes the factorial numeration system, I've heard. For the obvious reason, system, that these denominators are all factorials. This is 2 factorial, 3 factorial, 4 factorial, and so on. What about the following? What if we have something like Qn is equal to 10 for all n? So if Qn is equal to 10 for all n, then this is just a decimal expansion. So you can see this is just a generalization. And we'll see tomorrow other ways to generalize decimal expansions. Like there's some very, very interesting things that happen when you look at non-integer bases and can get really crazy, but in totally different ways. These can get really, really crazy, and we'll only talk about like a tiny portion of what happens with these. And actually, what originally brought me to Kyiv several years ago was that there is some work on Cantor series expansions here and some other even more general expansions. Professor Torben, for example, and Pratyaviti have done, and others have worked with them on related expansions, and their interest is very different from the reason I'm interested in these. There's typically more fractal-like stuff they're doing, and Roman could say more details, about this than I can, but I'm interested somewhat in fractals, but that's what their main interest is, and I'm more dealing with normality and some other conditions. So, anyways, we can do another one too. How about something like Qn is equal to 2 to the n? We could do this also, right? So our bases would be something like Q1 is 2, Q2 is 4, and so on. So what we'd end up getting is, if x is a real number, we'd end up getting some sort of expansion like the following. We would have something like x is a naught plus, and yeah, just to be clear, I didn't write this, a naught we can just say is the floor of x. So a naught plus something like a1 over 2 plus a1, a2 over, so 2 times 4 would be 8 plus a3. So 2 times 4, that's 8, times 8 would be over 64, and so on and so on. So there's nothing preventing you from having some sort of sequence of bases that goes off to infinity. And so you can imagine just when you have some sequence of natural numbers, there are all kinds of crazy things that could happen. And so I'll talk about this a little later because there are some, I think, potentially very deep questions that I want the answer to that are very much related to some questions, they're very much, let's say, logic or set theory questions that deal with what's happening for different crazy bases and what we can possibly say. But is the definition of Cantor series, is this clear right now? Can I move on to, so where I care about Cantor series is coming more from the perspective of normality. And this can get either really crazy or not so crazy depending on where you're looking. And this was originally examined by Hungarians, so like Renyi, Erdős, Turan, and so on. We're looking at normality. So at least this is initially, there are other authors as well. Let's say this is starting in the 1950s. And I guess I didn't mention when Cantor originally defined this, because this was a really long time ago. This was late 1860s. He was dealing with these irrationality criterion. So not new at all, but there's, like I said, there's still research kind of building off of the stuff he did in the late 1860s. So how would we even define normality for a Cantor series? So I want to propose, actually let me just kind of ask that, like you guys, what do you think? How would you define a normal number for a Cantor series that might work for, I give you a base and you say, okay, this is what a normal number is.
It depends on the sequence of the integers.
So the goal is I want to come up with a definition that will, anytime you give me a base, I kind of have some words where you can input that base and then the words actually make sense and give a reasonable concept. Right? So this is one of these things in math. It's not like you see in a textbook. Coming up with a good definition can be hard sometimes. And some of them are easy. There's one way that's actually really easy if you remember the last lecture. And there's another way that's not so easy. So normality, there's two different conditions that we said are basically representing normality. One is this definition in terms of blocks of digits, right? We have this kind of maybe more combinatorial or probabilistic perspective, like, the digit 0 shows up as often as it should, in air quotes, digit 1 and so on, and then blocks of digits and so on. And then there's another one in terms of uniform distribution. So we would also say that a number x is normal in base b if the sequence b to the nx is uniformly distributed mod 1. So we can look at either way. So let's say it'll turn out to a bit easier. Let's say we want to do something similar to, let's say x is normal if b to the nx is uniformly distributed mod 1. Right? Because essentially here you're taking as an input your numeration system. It's just a single integer. And so here we have a definition. We say you're normal if this holds. We know this is an if and only if, so we could even just take this as a definition. So does anyone see who's like a, say, undergraduate? Does anyone have an idea of how you would generalize this definition to Cantor series?
Just multiplying first n integers of this simple series.
Sequence, yes.
Sequence, I'm sorry.
Yes, exactly. So we can do the following. We can do the following. So let tqn of x equal qn minus 1, q1x mod 1. And then definition. X is q distribution normal. If the sequence tqn of x is uniformly distributed mod 1. Okay. So pretty natural, right? Just based on this idea from the last lecture. And I am going to prove right now in a very easy way that no matter which q you pick, you're going to have almost every real number being normal in the sense of it'll be a set of full measure. The set of normal numbers will be a set of full measure. And so recall this theorem, right? Recall. So recall if the sequence, we used an over there, I want to use a different thing. Let's say tn. Let's say if tn is a sequence of distinct integers, then tnx is uniformly distributed mod 1 for almost every x, or is uniformly distributed mod 1 almost surely, whatever language you want to use, so it's a set of full measure. So here, using this, I intended in the last talk to actually just prove that the set of normal numbers is full measure with this, but we'll just do the whole thing now with this definition. So all you do is, so theorem, given any q, and let's also call this set dn of q, because I don't want to just keep writing distribution normal, it's easier to have some notation. Given any q, the measure of, I'll just say it's full measure. dn of q is full measure. Proof. And this is just a one-liner. We just use this up here, letting tn be q1, q2 up to qn, and we're done. Right, since these integers qn, they're bigger than or equal to 2, each of these tn's will all be different. And you just use this theorem and it's all done. In particular, this also gives us a proof that the set of numbers normal in base b is full measure. So I didn't give a proof of that before. There's many reasons it's true, but this is a direct application of this theorem. So that's nice. Let me then ask, let's suppose that, let's say instead, we care about digits. Because, right, this is something that doesn't, I mean, you can kind of try to say something about digits here, but, well, these bases are changing and then the digits might mean different things at different steps. Is this necessarily telling you anything about digits? Well, we know in the case that qn is equal to b, it tells you a lot about digits, but maybe for some other crazy base, it tells you nothing. So that's going to be something we're going to try to figure out right now. And so let's just come up with an entirely separate, reasonable enough definition and see if the two coincide or not. So imagine if you had something like this. Imagine if you had something like qn, and there's a reason I am going to put something slowly growing here. Let's say qn is the maximum of 2 and floor of log of n. The reason for this too is we want to make sure that it's at least a sequence of bases, because if log of n is too small, we don't want to talk about something in like base 1 or base 0 or something weird like that. You know, so that's the only reason for that, just kind of technical point right there. Okay, so this is something that's going to infinity pretty slowly, but it's still going to infinity. So let me ask. Every single digit we're going to be able to see eventually, right? We're going to be able to see the digit 0, the digit 1, the digit 2, the digit 33, and I'm writing that because 33, and you're considering the digits to be integers. So that's not 3 followed by 3, that's 33. You have countably many symbols. Okay. So for this space here, how often, if there's any justice in defining normality, how often should we expect to see the digit 0?
Less often.
True.
Yeah, it's totally.
Maybe even a little bit easier is if we do this. Qn equals n plus 1. We go back to the factorial enumeration system. Maybe we can actually write it out in a nice way with this one. So we expect to see it less and less often, and that less often is going to 0, right? That's the problem, right? What do we do? How often do we expect to see 7 followed by 85? Also less and less often, but how would we, so we could say something like, well, the frequency of all of them is 0, but then that's no information. That's kind of an unsatisfying definition. So if you say the number of times you see 0 up to position n divided by n goes to 0, we could do like before, but I think that's a terrible definition. That doesn't really capture anything that's going on. So what about here? So let's look at this. This will be a little easier to start with, and then I can contrast the differences between these. So here we start with a 2, 3, 4, here's our QNs, 5, 6, 7, 8, and so on. So let's informally think like the following. So we have some place here for like, let's say AN. How often, if we're selecting real numbers uniformly at random from say 0, 1, how often should we expect to see the digit 0 in the first place?
Sort of cases.
Close. Half. So when we have a 2, you can either have a 0 or a 1.
I'm sorry, 0 or 1. Okay.
So for 0, just how many times we would expect to see this? Half of the time here. And then a third right here. So if we're counting up to like, let's say position n, right, we would have this n plus 1 base. So we'd expect to see 1/3 here, and we're assuming independence, right? We're just we can't assume that for all enumeration systems. We'll talk about that tomorrow. But here we have, we'll just assume independence for simplicity, and we'd expect to see 1/4 of the time, and so on, and then 1 over n plus 1 of the time we would expect to see the 0 by the end. Can anyone tell me approximately what this sum is equal to?
N ln n? No, just ln n.
Just log n plus some constant, basically. So this is approximately log of, and I'll write an n plus 1 just to be nice, but n plus 1 or n either way, plus a constant. And there's this Euler-Mastroni constant. It's about 0.57721. It's you get this interesting thing. These are the harmonic numbers, right? So you have a -1 because you don't have that. So it's going to be something like this gamma plus or -1, or I don't know, something along these lines. But anyways, yeah, the important part is that it's about log n. So the number of occurrences you would expect to see like an individual digit is about log n. And that's going to be true for all of them because, like, for example, if you look at the digit 7, well, it's going to be 0 plus 0 plus, okay, but then you see the base 8. And then here we have a 1 over 8 chance. So 0 over 7, 0 over 2, 0 over 3, and then a 1 over 9 and so on. So it can be the case that like you don't see something, it's not even possible to see it until a certain point. And then, but here it doesn't matter, right? Because it's just going to be log of n basically plus another constant. It's a different constant. Who cares? So we would think here, okay, individual digits. We could try to say some, one of the minimal things we'll need to have a normal number is that each of the individual digits occurs approximately log n times up to position n. But then what about blocks of digits? What about, for example, 0, 0? Say we had 0 followed by a 0. And the number of times we'd expect to see this in the first position would be 1/2 times 1/3. And then in the second position was going to be 1/3 times 1/4. And so on, up to 1 over n plus 1 times 1 over n plus 2. And so there's a bit of a problem, because this limit, right, the limit as n goes to infinity of this is finite. And limit as n goes to infinity of log n is infinite. So we expect, if things are nice, then we should expect to see any digit or any block of digits at least infinitely often. In fact, we want more than that. We want it to occur over and over again at some sort of regular, almost repeating pattern. And here, well, every single block of digits of length bigger than 1, you're only going to expect to see finitely many times. Okay, but then what about up here? So you would expect to see, so we could write this out, I don't know, 1 over Q1 plus 1 over Q2. This is for the digit 0, 1 over Qn. I don't know what the sum of 1 over the logs approximately is. I'm sure someone knows this estimate. I don't off the top of my head. But the important thing here is, so log of n is growing much slower than n, much slower. And if you look at something like, so the point is this is going to go to infinity, but then 1 over Q1, Q2 plus...
Because it's slowly varying, it should be n over log of n, yeah?
It sounds plausible. I would believe that.
Yeah, this is Karamatas theorem.
Okay. That sounds about right. I didn't want to say it with any confidence, but that sounds... So let's say that's approximately n over log n, which I completely believe. 1 over Qn plus 1, which is also going to infinity. So the important property is that log of n is growing slower than n to the 1 over k. That's basically what's happening here. So log of n grows slower. Let's say log of n divided by n to the 1 over k goes to 0 whenever k is, let's say, bigger than 0. Right, so basically log of n, it grows slower than 1 over n, it grows slower than square root of n, grows slower than cube root of n, and so on and so on and so on. So for this type of basic sequence, we would expect every single possible combination of digits to show up infinitely often. And we would have some description of it based on what happens when you take these tuples of products. And this particular case, n over log n, but you could also write something here as well.
M over square, log squared, yeah.
I can believe that as well. That sounds totally about right. So let's say, for kth one, n over log to the k of n, for example. But then there can be some other issues. What happens if Qn is equal to 1 plus n squared? Then nothing should show up infinitely often, or you would expect. I mean, things can, but nothing you would expect to. And so we get a little bit of and then you can also have it alternate. Maybe something does something for a while and then switches, and you can see how this gets kind of complicated. So basically, here's what we're going to informally take as the definition, and then I'm going to actually write it down formally with the motivation, is that we're going to say that a number is going to be normal if every single block of digits that you would expect to see infinitely often shows up as often as it should. So we only quantify over those blocks that are going to actually be shown up infinitely often. If you select, almost surely when you select a real number uniformly at random. And this has the funny consequence that when you take a definition like that, since you're only quantifying over these blocks, for this base, every single real number is normal. Because everything's just vacuously true. You're quantifying over an empty set. And what's the conclusion there is that this definition is, it's questions about this are not the right questions when you have a base that grows too quickly. Ask other questions. And Erdish and Renier did that. They asked other interesting digital questions in bases like this. But normality in the type of sense we're looking at here absolutely does not do any, it's just not something to even worry about when your base goes to infinity too quickly. Now, on the other hand, it still makes sense with this definition. You can still talk about something like, product of 1 plus n squares times x being uniformly distributed mod 1, and then it's a non-trivial condition. So already we see there's some difference in these conditions, but maybe it's the case that they live together nicely in some other places, because we know that they do, because in the case where the bases are constant, they're the same thing. And notice as well that what I said, it agrees with our base B expansion. In fact, it gives a little bit more insight, because when we talk about normality in base B, which blocks are we quantifying over? We're quantifying over those that we expect to see infinitely often. And if you're in base 10, for example, we don't have the digit 73. So we don't quantify over a block with the digit 73 because we can't see it. So we're not going to expect to see it infinitely often. So in fact, it even tells you kind of what language you're going to have in base B if you just take this broader definition. So if we want to formally write this down, we let n sub n q of b comma x be the number of times b occurs in the Q Cantor series expansion. Q Cantor series expansion of x up to, I know you could say starting position n, doesn't really matter. Okay, so we have something to count how many times, and we want to talk about the growth rate of this function, that it should be what we get from the bases. So how do we talk about the expected growth rate? And this is just entirely an expected value. We only add 1 when we can possibly see it. So let's suppose that b is equal to b1, b2, up to b to the k. Okay. And then we're going to say that, let's say, if you're given q equal qn, we're going to define I sub j of b is equal to 1 if b1 is less than qj and b2 is less than qj plus 1 and bk is less than qj plus k minus 1 and 0 otherwise. So this function, it just spits out a 1 if you can possibly see your block at that position. That's all that is, just written in formally, and then a 0 otherwise if you can't see it. And then we're going to write qn of b is going to be the sum of I from j equals 1 to n of I sub j of b over qj plus 1 up to qj plus k minus 1. Okay, so this is, you can think of this as just an expected value. We say that if you can actually see block B at position j, maybe you can't, then you say there's a 1 in qj chance the first digit matches times a 1 in qj plus 1 chance the second digit matches, and so on and so on. So definition. And I'm going to actually break this up a little bit further, and you'll see why in a little later. X is q normal of order k, if for all b where the length of b equals k and qn of b goes to infinity, so we're only quantifying over blocks where the expectation is going to infinity. We have the limit as n goes to infinity of n sub nq of b comma x over qn of b is equal to 1. And this completely matches up with our base 10 normality definition, because in base 10, we divided by n and had the right-hand side be b to the minus k, and all we're doing is dividing both sides by b to the minus k. So we just get like a expectation as nb to the minus k down there. And we're going to call this set nk of b, nk of q. And then we say that x is q normal X is Q normal if X is a member of, let's say, n of Q, which we define to be equal to the intersection from K equals 1 to infinity of nk of Q. So in other words, is Q normal if it's normal of all orders? You know, if you quantify over blocks of length 1, length 2, length 3, and so on. I didn't write this sort of a distinction between the different orders in base B, but there's a reason why we care here, because some completely wacky and crazy things start to happen. Okay. So, I'll just write this question just because I don't want to forget it, but let me just say, for those who know what Borel sets are not, here's a big question that I really, really, really want to know the answer to. So, open question. Is the set of all Q, right, and n2 to the n, so this is in the bare space, such that n of Q equals dn of Q, a Borel set. So I'll probably come back to this again in a couple talks, but here I'm basically kind of asking, is there any reasonable characterization of when these two notions coincide? So I have, and as well as some of my co-authors and other people, we have some sporadic conditions under which they're equal and which they're not equal, but is there some full, reasonable enough characterization that only involves countable quantification? And that's what I'm asking for, and I have no idea. So let's look at what can kind of go wrong here. Yes?
What is NQ?
So what is NKQ?
This right here?
Yeah.
No, the set of numbers that are Q normal of order K.
Okay, thank you.
So this is right here. And then you're saying you're normal if you're normal of all orders. So crazy, crazy things happen here, and we definitely want to know about these when we get to the descriptive set theory part. Interesting things will happen. Okay, so just kind of a basic thing. If, so theorem, suppose that, let's say, limit as capital N goes to infinity of 1 over n sum from n equals 1 to n of 1 over qn is equal to 0, then x is q, let's say x equals a0, point a1, a2, and so on, is a member of dn of q, so the set of q distribution normals, if and only if the sequence an over qn is uniformly distributed mod 1. And we'll take this as an exercise. And this is due to, this is one of these Slovakian names, and I forget where they put the accents on everything. So he was in Tibor Shalat, I think, is maybe something like this, and I don't remember. But he was in Bratislava. I don't think he's around anymore. But it turns out actually that this is true if and only if this happens. But what this is basically saying is that, unlike with the decimal expansion, you can only look, all you need to do for distribution normality, if your base is either going to infinity or going to infinity except on a set of density 0, is you need to check, does the sequence of your digit over your base, is that going to be uniformly distributed or not? And just this, I think this should be reasonably plausible because, right, if you have something like, right, you're looking at, like if you shift, like tq n of x, right, this is going to be an plus 1 over qn plus 1 plus an plus 2 over qn plus 1, qn plus 2, and so on. So you want to know when this sequence is uniform, if you take this sequence of tqn of x, you want to know when that's uniformly distributed. This is the same thing as asking when that's uniformly distributed. And if qn plus 2, qn, for example, is going to infinity, then the ratio between this term and this term is going to 0. So essentially, everything here is becoming less and less significant, and this is becoming all that really matters. I mean, that's just very, very hand-wavy. Of course, you need to prove it, but that's just kind of the intuition here. And what does this condition here mean? This can be interpreted as saying that either limit of Qn is infinity, or maybe there's just a sequence of zero density on which it's bounded. Those who've looked at some ergodic theory may recognize some similar looking conditions, especially when dealing with weak mixing. But you can just kind of ignore this and just think about, let's say, or Qn goes to infinity. And so this is a really useful theorem. Like I said, a lot of times the most useful theorems are also actually very easy to prove, and so this one's just an exercise. But let's use this to construct an example where Qn goes to infinity, but not too quickly, where we can cook up a number that's Q distribution normal, but not Q normal. And it's very easy to do. So we look at the following. We let the sequence Qn be given by this, and An be given by this. So we're going to say something like 2, 4, 4, 4, 6, 2, 4, 4, sorry, 6, 6, 6, 8, 8, 8, 8, and so on. And here we'll go 0, 0, 2, 0, 2, 4, 0, 2, 4, 6, and so on. So basically we're saying we let x equal the sum of an over q1 to q1. Okay, so we just use this theorem up here. This sequence, the nth digit over the nth base, is going to be uniformly distributed by mod 1. This is just what we talked about in the last class. You know, you have even numbers up here, so an over qn just looks like 0 over 1, 0 over 2, 1 over 2, 0 over 3, 1 over 3, 2 over 3, and so on. So here, an over qn, based on the exercise I gave on Tuesday, is uniformly distributed mod 1. If you didn't do the exercise, I recommend doing it to get a feel for it, but it should be believable. But can everyone immediately see why this number is not going to be normal? It's very badly not normal. It's missing every odd digit.
No, yeah, odd digits.
Yeah. So there's no odd digits. So x is in the n of q minus n of q. And how fast does this base grow approximately? So Qn, in this case, Qn is approximately some constant times what?
Log n.
Not log n, it's faster than that. A lot faster than that. Square root of n. Kind of like inverse of a triangular number, sort of. Check that. So, so it's going to infinity, but it's not going to infinity so quickly that we would expect there not to be any, you would expect both blocks of digits, 1 and digits 2 to be showing up, at a reasonable rate. Digits of length 3 after them, then, no idea. I mean, well, not no idea, it'll just be finitely many times 2. So. What about the other way around? This is harder. So we want to restrict to basic sequences that are, say, not going to be like n squared, nothing that's growing too quickly. But any idea how you would construct something that's normal but not distribution normal, but not in some sort of trivial and silly way? I would still call this like not trivial and silly. I mean, this is a fundamental problem that happens. In fact, I'm going to claim that you can do even crazier things. Like, let's say I am going to make, say, x, where x is q normal, and tqn of x goes to 0. Mod 1 at least. So not only is it not uniformly distributed, it actually goes to 0. Only one accumulation point. So there are some different levels of efficiency. So the first example of this was with my co-author Chris Altamare. And it was some 20-page construction with a lot of detail, and we got something a lot more efficient. How are we on time? Are we already? Oh, okay. All right. Well, what you can do, so I'll just say rather quickly what you can do with this. There's a function we call psi. Okay, this is something interesting. I will write this down. Let's say x is equal to point a1, a2, and so on in base p. And we write that psi pq of x is going to be the sum from n equals 1 to infinity of the minimum of an and qn minus 1 over q1 to qn. So what we do is we take an expansion in base p, and if digits are too big, we just cut them down to the biggest they can possibly be. So for example, like if you have 1/7 in base 10, 1, 4, 2, 8, 5, 7, and so on. And let's say this is, so base P is just the sequence 10, and let's say Q is the sequence 3. In this case, psi PQ of 1/7. Okay, what's this going to be in base 3? That's 0.1, that's not a problem, but then this gets cut down to a 2, this gets cut down to a 2, that gets to a 2, and then, it changes some. Basically, anytime you have a digit that's 3 or bigger, you knock it down to a 2. And it's kind of fun. There's a lot of interesting fractal properties that the graphs of these functions have, and what we care about is that this lets us do all kinds of constructions in a much easier way. So there's a basic theorem here is, let's suppose, I think it's Qn goes, let's suppose both Qn and Pn go to infinity. Let's suppose this is true. And let's say B is any block of digits. Then we have that the number of occurrences up to position n in base P of B in X, let's start with Q, of B in psi PQ of X is equal to the number of occurrences up to position n in base P of B in X plus big O of 1. And this is another thing I claim it's like super simple, and there's nothing to prove here, but it's really useful. You can so all that's really going on here is if Pn and Qn are going to infinity, like you fix a block of digits, like 1 followed by a 5 or something. Well, we only really need Qn goes to infinity. So if Qn's going to infinity, then these sorts of bad positions here, you're only going to see finitely many of them, right? So maybe Q1's going to infinity, well, it's not going to dip below 7 after some point. So this is where we get this big O of 1 term right here. And so I'll show exactly how to solve this problem up here by just cooking up the right basic sequences P and Q. So all we do is we come up with some Q, so let Q be such that I guess it would be any basic sequence. Yeah, let's let Q be a basic sequence. It doesn't matter even, a basic sequence. And then we define P as follows. So let Pn be the maximum of 2 and floor of log Qn. And my claim is going to be, so if we let X be a member of n of Q, and I didn't prove this yet. You need other theorems from probability theory to always show that n of Q is full measure, but it's always full measure. The best results use a version of the law of the iterated logarithm. But let X be a Q normal number, and then I'm going to define, so we let Y be equal to, and we're going to say psi, let's say Q comma P composed with psi P comma Q of X. So the first thing we do is we take X, this is a Q normal number, and the digits are expressed, right? You can express them in base Q. And then we do this process where we bump them down to base P, which is looking like log of base Q. So let's say Q is a basic sequence where Qn goes to infinity. We need this. So if Qn is going to infinity, then Pn also goes to infinity. Okay. And then we just say, okay, well, those digits, they haven't exceeded. So at this point, right, the digits are less than or equal to something like log of Qn. When we apply this, and then we just say, we'll go back to base Q. So because of this result right here, we know that the number of occurrences for any block, NQ of B comma psi PQ, NQ, let's say in Y, is going to be N Q of B and X plus big O of 1. So there's only some constant number that we lose in the beginning by doing this process. So what we end up getting is that Y is Q normal, but the nth digit of Y is going to be less than or equal to log of Qn. So we have this weird scenario where you have all this stuff that's like really going on with small digits. Your bases are getting larger and larger and larger, and kind of the limb soup of your digits is going to infinity, but it's going to but that limb soup is climbing much, much slower than your base. In particular, you're going to have that TQn of Y is going to go to 0, right? Because this is going to be something like less than log of Qn plus 1 over Qn. And log of Qn is dominated by Qn, so this is going to go to 0. Okay. Does it make sense what I did there? And cooking up things with this particular function is one of the most important tools, at least for this class of bases, where the bases are going to infinity. And see how much time, because I don't want to go too far over. So there's a whole, I want to also remark as well that for this number Y, is we note that Y is going to be in the member, as a member of the set of, let's say, Z in N of Q, such that N times Z is not a member of N of Q for all N in, let's say all N in 2, 3, 4, and so on. And so this is a very weird set we'd expect to be empty, because remember in base B, whenever you multiply by a rational number, you get you multiply a base B normal number by a rational number, you get a base B normal number back. So this really, really weird stuff is starting to happen with these types of normal numbers, because we not only proved that by this construction, we did a few things at once. We not only proved that being normal for one of these bases where Qn is going to infinity, that doesn't guarantee that your distribution normal, but moreover, we've shown that even integer multiplication does not preserve normality, which is a big difference with one of these properties we had from the last talk. So part of why I was asking this question before about like when these notions of normality coincide, is this a Borel set, and why do we want to know this? So part of what's happening is that it feels like a lot of the theory of normality is depending on this equivalence. So we had this proof from the last talk where proving that that rational addition preserves normality. Well, that was using this connection between this theory of uniformly distributed sequences and just base B normality. You have this connection between the two. And here we don't have that connection, and then a lot of stuff starts to be kind of pulled out by the seams and go a little bit crazy. And there's a lot of other really, really interesting stuff I would like to show, but we don't have enough time. So I wanted to mention there's another class of basic sequences that has started to have been studied, and there aren't any papers on this yet. There's several that are in preparation at the moment. But what happens if you were to suppose that your basic sequence Q itself was something like a normal number in base B? And actually very interesting stuff starts to happen, and you actually can prove a lot of things. So there's kind of the question of what generality should I prove a base B normality result to? So you have a theorem about normal numbers in base B. Do you prove it in something like Qn equals log n. Well, probably it's not going to hold true because things live in a totally different way in this base. But what if you have a Champernowne number? So like, 0.1, take this, 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and whatever. Okay. This is a base 10 normal number, so let's form a base from this. Well, it doesn't make any sense to talk about base 0, so we want to add 2 to every digit to form a new base. So we would now form a base as follows. This would be 3, 4, 5, 6, 7, 8, 9, 10, 11. So this would be 11, and then 2 plus 1 is then 3, and then this is 2, and then 3, 3, and so on. So this basic sequence here, this is basically like the Champernowne number, but you're relabeling it. It's just to have it make any sense at all. And so it turns out you can actually start to develop some of the theory from normal numbers in the case where you have basic sequences that are generated in some dynamical type of way. And we haven't talked about ergodic theory, but there are some hidden dynamical systems going on with base B normality. And there's, you can say even more when you have something that we call like a low entropy sequence. So there's the Thuy-Morse sequence. Has anyone heard of Thuy-Morse? You can actually say a lot more here. So does anyone know this sequence? Maybe computer science? Okay, so we start with, we can say start with a 1. And then we can take the negation of this and concatenate it. Then we take the negation and concatenate it again, so 0, 1. And then we take the negation and concatenate, so 0, 1, 1, 0, and then so on and so on. Maybe you talked about it, maybe not, but this is, you can Google Thuy-Morse. And if you take your basic sequence to be Thuy-Morse, you'd want to add 2, so it would be 2 and 3s, for example. Then it turns out actually that normality and distribution normality are equivalent. They're actually not equivalent for this base, but there's some other stuff you can say. So depending on the type of properties, so these will be something called generic points for some type of measure preserving system. Not to worry exactly what that means, but depending on a certain property called entropy from that dynamical system, there are certain results that can be extended there and some that can't. And this is part of an ongoing project with my postdoc, Sohail Farhangi. And it relates to this paper that Roman and I have been working on that we deal some with these types of basic sequences. And there are some things that you can say. So, like I said, I could really talk a lot more on this topic, but I think that maybe now is a good ending point, and we can go to other enumeration systems tomorrow. So.
Questions? Yep. Any question? Yeah, please.
You have set this set on the upper.
Yes.
Is it full measure or not?
It's full Hausdorff dimension. It's 0 measure, but full Hausdorff dimension. And that's interesting that it would still have big Hausdorff dimension. And I also, I may as well even write this as well because this was something weird. I was setting this up. You can imagine if your normal, imagine if a number in base 10, if all the blocks of length 3 show up as often as they should, like 0, 0, 0 up to 999, then you can show that all the individual digits, 0 through 9, show up as often as they should with frequency 1 and 10, and also of length 2. For Cantor series, it gets totally, totally crazy, and it turns out that you can, for example, the set of numbers, let's say the intersection, the set of numbers, normal of order of even orders, nk of q, but not normal of odd orders, is not empty set. I think it also, under some conditions, it'll have full Hausdorff dimension. I, by the way, don't know how to prove this in the case that we put the odd numbers here and the even numbers here, although surely it's true. If we put prime numbers here and composite numbers here, then this is really, really weird, right? So you have something that's, you can have numbers that are normal of orders 2, 4, 6, 8, and so on, so all blocks of even lengths show up as often as they should, but not of odd lengths. And this is very weirdly connected to some, let's say, a question in algebraic geometry. And I want to write something down. And this is going to look like something let's say it looks like just an algebra question, but I don't know how to do this. I've been asking people about this for about 13 years now, since 2012. But it's very simple to write, so let me just kind of write this down to see if anyone wants to work on this, but it looks like an algebra question. Let t be a natural number, and then we consider C1 plus C2 plus C3 plus dot 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 plus CT equals 2t. C1, C2 plus C2, C3 plus, and I want to emphasize that there is not that much symmetry here, so I'm not saying all pairs, I'm saying only adjacent pairs. Just to be clear, that's very important. And C1, C2, C3 plus dot 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 plus CT minus 2, CT minus 1, CT equal 2t, and so on down to C1 to CT equal 2t. So you're looking at points on this algebraic variety or nonlinear system of equations, however you want to call it, and then proof. This is the problem that I don't know how to do. There exists a solution, C1 to CT, in the set t to t plus 1 cross 1 to 1 plus 1 over t minus 1, so the t minus 1. So the first coordinate's about as big as t, and then the second, all the rest of the coordinates are pretty close to 1. Numerically, we verified this with Newton's method up to about t equals 110. We believe it's true. A simple case for t equals 3 would be C1 plus C2 plus C3 equals 6. C1, C2 plus C2, C3 equals 6. C1, C2, C3 equals 6. You can do this one by hand. It's not that hard. Starting at t equals 4 and so on, you don't have any solutions in radicals. So you can do some stuff with Galois groups and all that. If anyone's interested, I can write out how it turns out. So if anyone has any idea how to prove that this system of equations will always have a solution somewhere in this region, I would be very interested in hearing. I've heard many starts of ideas, but everyone runs into a brick wall at some point. How is that related to Cantor series and things like this? That's 1 or 2 lectures worth of explaining. If anyone wants to know, I can explain it, but I promise there actually is a connection to normality of different orders, and there's a way that this pops up in some sort of surprising way. So I wanted to mention that. But anyways.